A mathematical equation is a statement that equates an expression to another expression. Symbolically, an equal sign between the two expressions represent an equation. If the expression on both sides of equal to signs are polynomials of degree, for example 1 or 0, as whatever determines the truth of the equation, then the equation is said to be a linear equation. A general linear equation in two variables is of the type ax plus by equal to c. Likewise, an equation in the form of ax plus by plus cz is equal to d is a linear equation in three variables. That is, the variables or the unknowns are always in linear powers. Geometrically, a linear equation in two variables represents a line in a two-dimensional plane. Similarly, a linear equation in three variables represents a plane in a three-dimensional space. A system of linear equation is a finite set of linear equations in the given variables. In other words, a linear equation system is a collection of linear equations that are dealt all together at once. Geometrically, a linear system of two equations in two variables is graphed as two straight lines in two-dimensional plane which can be intersecting, parallel or coincident. This geometrical view of system of linear equation further gives us a clear idea of the solution of the linear system, which is the all-time goal any algebraist is working on. A most common real life example of a linear system is a business organization where the output is proportional to the input. This situation is mathematically modeled by a linear equation. For example, regarding the applications of linear system, one can see that this mathematical concept has got wide applications in diverse fields. In some fields, the nature of equations appearing in a system may be non-linear, but in course of the analysis, linear equation system will emerge. It is preferable because of the simplified nature of linear system, which are quite easy to solve. More elaborate techniques are needed if the number of unknown increase in a linear system. However, by use of programming in computer science, it is now possible to solve large system of equations very quickly and accurately. Linear system can be very commonly seen in problems dealing in engineering, dynamics, electric circuits, market models of specific commodities, business organization, optimization problems, etc. In this module, we introduce the concept of system of linear equations. Their formulation subjected to the restrictions and constraints describing a situation and illustrate the concept by considering practical problems in economics. After reading this module, you shall be able to 1. Identify a linear equation of n variables or unknowns. 2. Identify and formulate a system of linear equations in n unknowns. 3. Solve the system of two equations in two unknowns and verify a given set of n values to be the solution of the linear system. 4. See a geometrical view of a 2 into 2 linear system representing a collection of two equations in two unknowns and solving the system by graphical method. 5th, relate the concept of linear system of equations to some of the well-known concept of economics and formulate its mathematical model. First, we shall understand linear equation. A linear equation in n variables or n unknowns x1, x2 till xn is an equation representing a relation between the n variables or unknowns. In general, a linear equation in n variables is of the form a1 x1 plus a2 x2 plus it continues to an xn, which is equal to b. This is equation 1, where a1, a2, an are real constant. Here b is equal to 0, then the equation is said to be homogeneous linear equation, and if b is not equal to 0, it is a non-homogeneous linear equation. For example, 2x1 plus 3x2 plus 5x3 is equal to 9 is a linear equation in three unknowns x1, x2 and x3, whereas ax is equal to b is a linear equation in one unknown where a and b are real constants. Note, the powers of variables or product of variables do not occur in linear equation. Also, any exponential, trigonometric or logarithmic function, if it exists in the equation, has to have a constant argument and not have the unknown variables as its argument. For example, x1 squared plus x1 x2 plus x3 is equal to 1 and tan x1 multiplied by x2 plus x3 equal to 2 are not linear equations. However, tan A into x1 plus x2 is equal to 2 is a linear equation where A is a real constant. Solutions of a linear equation. A set of n numbers, that is C1, C2 to Cn, is said to be a solution of the linear equation 1 if x1 is equal to C1, x2 is equal to C2, xn equal to Cn satisfies equation 1. For example, x1 plus 2x2 is equal to 3 has 0, 3 by 2 and 3, 0 as its solution. In fact, many more solutions exist for the linear system, as 1, 1 and 2, half are all solutions of this system. System of linear equations. A finite collection of linear equations in the unknown variables x1, x2, xn forms a system of linear equations. In general, a system of m equations in n unknowns is of the form a11x1 plus a12x2 plus a1n is equal to b1. Then a21x1 plus a22x2 plus a2nxn is equal to b2, and so forth till am1nx1 plus am2x2 plus amnxn is equal to bm. This is signified as equation 2. Here aij, bi, I is equal to 1 to m, j is equal to 1 to n. These are all constant. The constants a, I, j represent the coefficient of xj in the ith equation. For example, 2x1 plus 3x2 is equal to 5. 4x1 minus x2 is equal to minus 2 is a 2 into 2 linear system of two equations in two variables. Similarly, consider the 2 into 3 linear system. x1 plus x2 minus 5x3 is equal to 6, minus x1 minus 4x2 plus x3 is equal to 8 of two equations in three unknowns. Solution of a linear system. Consider the m into n linear system given in equation 2. A solution to equation 2 is a set of n numbers, C1, C2 to Cn. If x1 is equal to c1, x2 is equal to c2, and xn is equal to cn satisfies each of the m equations of the linear system in equation 2. For example, consider the system x1 plus x2 is equal to 2, 2x1 minus 3x2 is equal to minus 1. This is a system of two equations in two variables. Here x is equal to 1, y is equal to 1 is a solution as 1, 1 satisfies both equations of the system. For example, the linear system x1 plus x2 equal to 4 and 2x1 plus 2x2 is equal to 2 has no solution, whereas the linear system x1 plus x2 equal to 4 and 2x1 plus 2x2 equal to 8 has infinitely many solutions. Consistent linear system. A linear system that has at least one solution is called a consistent linear system. A consistent system can have a unique solution or infinitely many solutions. For example, the linear system x1 plus x2 equal to 2, 2x1 minus 3x2 is equal to minus 1 has a unique solution given by 1, 1, whereas the linear system x1 plus x2 equal to 4 and 2x1 plus 2x2 equal to 8 has infinitely many solutions. Inconsistent linear system. A linear system that has no solution is called an inconsistent linear system. For example, the system x1 plus x2 equal to 4, 2x1 plus 2x2 is equal to 2 is an inconsistent linear system. As discussed in the introductory section, a linear system of two equations in two unknowns can be graphed as two lines in a two-dimensional plane where the lines can be parallel, intersecting, or coincident. Similarly, a 3 into 3 system of three linear equations in three unknowns can be graphed as three planes in a three-dimensional coordinate system, which can be either parallel, coincident, or intersecting. In general, a system of m equations in n unknowns can be graphed as hyperplanes in n-dimensional plane. However, the scope of a module restricts us to a system of two or three unknowns at the most. Of these two, a system of two unknowns can be easily solved and viewed geometrically. For a system of three unknowns, we will prefer using other techniques which would be discussed in detail in the next module on linear system of equations. Consider a 2 into 2 linear system with two equations in two unknowns. Clearly, its geometrical view can be very easily and clearly seen in a two-dimensional plane. As each system of equation represents a straight line in a 2D, so each graph will contain two straight lines. Now there are three possible cases that arise. One, the lines representing the linear equations are parallel. If L1 and L2 are the geometrical representations of the equation of the linear system, then the following figure shows the case when lines L1 and L2 are parallel. In such a case, there does not exist any solution to the system. Such systems are inconsistent. The lines representing the linear equation intersect at a single point. In this case, the lines L1 and L2 representing the equations of the system. In such a case, a unique solution exists for the system, and the solution is the unique point of intersection of lines L1 and L2. Such systems are consistent with the unique solution. Third, the lines representing the linear system are coincident. In this case, the lines L1 and L2 representing two equations of the linear system coincide with each other. In this case, each and every point is common to both the lines, and therefore each point has to be a solution to the system. Clearly, the two lines are altogether the same. So each and every point of the common lines has to be a solution. As the line in itself has infinite number of points, so the solutions in this case would be infinitely many in number. This again is a case of consistent system. For a system of three or more unknowns, the geometrical approach is not preferable, as the view in higher dimensions will not be manually easy. In fact, the geometry in higher dimensions might make the concept tedious and cumbersome to understand. So for a system of three or more unknowns, we will use other solution techniques. So we now illustrate some examples of a 2 into 2 linear system which can be very easily solved both graphically and analytically. Solve the system of two linear equations in two unknowns. X1 plus x2 is equal to 2. 2x1 minus 3x2 is equal to 6. Clearly, by eliminating one of the unknowns, we can easily get the solution. For this, we multiply the first equation by 3 and add the resulting equation with the second equation. That is, 3x1 plus 3x2 is equal to 6. And we have 2x1 minus 3x2 is equal to 6. This gives 5x1 is equal to 12, or x1 is equal to 12 by 5, and x2 is equal to minus 2 by 5. Also, by substituting the value of one of the unknowns from one of the equations into the other equation, we can get the same solution. Now, if we plot the two lines representing two equations of the system, we get the following graph. Graphically, it can be seen that the point where the two lines intersect lies on both the lines, and so it satisfies both the equations simultaneously. Hence, the set point is the unique solution to the system. Consider the following system of two equations in two unknowns. x1 plus x2 is equal to 3, x1 plus x2 is equal to 6. Solution. Using the elimination method, if we subtract the two equations, we get 0 is equal to 3, which is absurd. So mathematically, no solution exists for the given system. Such a system is an inconsistent system. If we plot the equation, we get the following graphs. Consider the following system given by x1 plus x2 is equal to 2, 2x1 plus 2x2 is equal to 4. Solution. If we use our elimination method to solve the system, we get 0 is equal to 0, which is mathematically true. But if we observe carefully, second equations of the system is same as the first equation. If we divide the second equation by 2 on both sides, so the system is actually consisting of just one and not two equations. Since the second equation is equivalent to the first equation, the system would be called redundant. So the system has one equation in two unknowns, which can provide us with a solution in terms of one of the unknown variables. Assigning arbitrary values to one unknown variable would every time give a value to the other unknown variables, leading to a collection of infinitely many solutions. Graphically, if we plot the system, we get Now each and every point on the line plotted satisfies both the equations of the given system. Hence, the result is a set of infinitely many solutions. This is also considered as a consistent but redundant. Now we shall discuss the applications of linear system. First, national income analysis. Consider the economy of a nation with I as national income, E as consumption expenditure, and EO constant as the government expenditure, and IO constant as investment. As stated above, EO and IO remain constant, whereas national income I and consumption expenditure E are the unknown variables. Considering the equilibrium in national economy, we know it is attained if national income is equal to the total planned expenditure. Mathematically, this can be written by means of a linear equation in two unknowns I and E. That is, I is equal to E plus EO plus IO. Also, the consumption expenditure E and national income I are directly proportional to each other. Hence, they can be related by means of a linear function of the form E is equal to A plus BI, where A and B are constants representing the autonomous consumption, expenditure, and the marginal consumption propensity, respectively. So, the complete national income analysis can be represented by the 2 into 2 linear system of two equations in two unknowns I and E. That is, I is equal to E plus EO plus IO. E is equal to A plus BI, or I minus E is equal to AO plus IO, or minus BI plus E is equal to A. As discussed above, this 2 into 2 linear system can be solved by elimination techniques or substitution technique or even the graphical method if the values of constant A, B, E, O and IO are known. Applying the substitution technique, we substitute the value of E as A plus B I from the second equation into the first equation to get I is equal to A plus BI plus EO plus IO, or in bracket 1 minus BI is equal to A plus EO plus IO, or I is equal to A plus EO plus IO divided by 1 minus B. Using this value of I, we get the value of E is equal to A plus B bracket open, A plus EO plus IO divided by 1 minus B bracket shut. The value of I and E obtained in the solution represents the equilibrium national income and the equilibrium level of consumption expenditure. Since both the equilibrium values have 1 minus B in the denominator, so we need to put the restriction B is not equal to 1. That is, marginal consumption propensity is assumed to be a positive fraction less than 1. That is, B lies between 0 and 1. Also, it has to be assumed that A is greater than 0. So, we need to associate the condition A greater than 0 and B lies between 0 and 1 to the linear system representing national income analysis. These conditions will ensure that the solution I and E of the system is positive. Two commodity market model. Let us consider only two commodities related to each other in a market. We assume that demand and supply function of each of the commodities are linear. Let the numerals 1 and 2 represent the two commodities, x1 and x2, be their quantities demanded, y1 and y2 be their quantities supplied, and z1 and z2 be the prices of the commodities 1 and 2 respectively. As demand and supply functions are assumed to be linear, so we can relate the demand and supply functions of a commodity in terms of its price as follows. X1 is equal to AO plus A1 Z1 plus A2 Z2, demand function of commodity 1. Y1 is equal to BO plus B1 Z1 plus B2 Z2, supply function of commodity 1. X2 is equal to CO plus C1 Z1 plus C2 Z2, demand function commodity 2. Y2 is equal to DO plus D1 Z1 plus D2 Z2, supply function of commodity 2, where coefficients A's and B's, C's and D's are coefficients related to demand and supply functions. Now we know for the market to be in equilibrium, demand for each commodity must be equal to its supply in the market. That is, we need to have X1 equal to Y1 and X2 equal to Y2. That is, AO plus A1Z1 plus A2Z2 is equal to BO plus B1Z1 plus B2Z2. CO plus C1Z1 plus C2Z2 is equal to DO plus D1Z1 plus D2Z2, or AO minus BO plus A1 minus B1 into Z1 plus A2 minus B2 into Z2 is equal to 0, or CO minus DO plus C1 minus D1 into Z1 plus C2 minus D2 into Z2 is equal to 0. Let us write AI minus BI is equal to alpha I. Ci minus di is equal to beta I. For I equal to 0, 1 and 2, using alpha I and beta I in the system, we have alpha 1 Z1 plus alpha 2 Z2 is equal to minus alpha 0 and beta 1 Z1 plus beta 2 Z2 is equal to minus beta 0. This represents a linear system of two equations in two unknowns Z1 and Z2. The solution to this system gives the value Z1 and Z2 of equilibrium price of commodity 1 and 2. However, we need to associate some conditions and restrictions of AI, BI and CI and DI and eventually or alpha 1 and beta 1 to ensure the positivity of the price values Z1 and Z2. N commodity market model. Generalizing the above example for a market with N related commodities with quantity demanded as X1, X2 to Xn for each commodity with quantity supplied as Y1, Y2 to Yn correspondingly. Again, let Z1, Z2 to Zn be the prices of N commodities. Now, as each of the commodity demanded Xi and each of the supplied commodity Yi are functions of prices Z1, Z2 to Zn, that is Xi is equal to Xi bracket open, Z1, Z2 to Zn bracket shut, and Yi is equal to Yi bracket open, Z1, Z2 to Zn bracket closed, where I is equal to 1, 2 to n. Again, for market equilibrium, Xi is equal to Yi, I is equal to 1, 2 to n. So Xi bracket open, Z1, Z2 to Zn bracket shut minus Yi bracket open, Z1, Z2 to Zn bracket closed equal to 0. Now the difference of the corresponding equations would clearly be again a function of prices Z1, Z2 to Zn, say denoted by Ti bracket open, Z1, Z2 to Zn, comma, I is equal to 1, 2 to n. Hence, the above system can now be represented by Ti bracket open Z1, comma Z2 to Zn bracket closed is equal to 0, where I could be equal to 1, 2 right up to n. This represents a system of n equations in n unknowns Z1, Z2 to Zn, which are the prices of n commodities. Now, depending on the values of the constants relating quantities and prices, the solution of the system may or may not exist. Though again with suitable restrictions imposed on the constant, the solution to the system indeed exists. Hence, the equilibrium prices for n commodities of markets can be obtained from the above generalized n into n linear system. Let us now summarize what we have learnt in this module. A general linear equation in n variables is of the form a1 x1 plus a2 x2 plus a3 x3 continues till an xn equal to b, where a1, a2, an are all and b are all constants. A set of n values x1 equal to c1, x2 equal to c2 and xn equal to cn satisfying a linear equation is called its solution. A collection of n equations in n unknowns forms an n into n linear system, which is given by a11 x1 plus a12 x2 plus this continues to an xn is equal to b1. let me repeat, A11x1 plus A12x2, it continues to A1n xn, which is equal to B1. Then we have A21x1, A22x2, this continues to A2n xn, which is equal to B2. Similarly, AM1n x1 plus AM2x2, which continues to AMN xn, which is equal to Bm. Here Aij, Bi, where I varies or moves from 1 to m, j varies from 1 to n are constant. The constants Aij represents the coefficient of xj in the ith equation. A set of n numbers satisfying all the n equations of the system simultaneously is called a solution. A system may or may not have solutions. If a linear system has a solution, it is called a consistent system, otherwise it is inconsistent. A consistent system may have a unique solution or infinitely many solutions. Geometrically, a linear equation in two unknowns is graphed as a line in two-dimensional coordinate system, and a linear equation in three unknowns is graphed as a plane in a three-dimensional coordinate system. Geometrically, for a 2 into 2 linear system, a unique solution is obtained by a pair of intersecting lines. No solution if lines are parallel, and infinitely many solutions if the lines are coincident. Various applications of linear system of equation can be seen in economics, for example, mathematical model of national income analysis, n commodity market equilibrium model, etc.